Hey, grade 12s. Today, as I like to say, we're going to start to learn to count. Throughout your years so far, you've definitely had experience counting. You might count the number of baskets you score at a basketball game. You might count the number of cars that pass you on the highway when you're traveling with your family. You might count the number of ways that your significant other is just absolutely awesome. There's so many things that we can count. But when it comes to counting numbers that are really big, there are often methods or shortcuts of doing this in an organized way. And that's what this unit's all about, is learning how to count. And probably the most important thing to help us to learn to count is the fundamental counting principle, which is the very first thing we're going to learn in this unit. So here we go. A certain type of cell phone makes a sound, vibrates, and flashes a light when a text arrives. The sound could be, so we've got sound as the first thing. The sound could be a beep, a buzz, or a chirp. And we'll keep it simple for vibration. It can either vibrate slow or fast. Okay. Now, as far as the light goes, the light, we're going to have a few more choices. So for the light, we have white, yellow, blue, or red. So the question that I have for you is, how many different ways can somebody choose a sound, vibration pattern, and light flash? How many choices do we have? That is the crux of today's lesson. Okay? So, how are we going to find out the answer to that? Well, what we're going to do for this question anyway is we are going to build a tree diagram. So, we'll start off with the sound. There's 3 different sounds. So, let's just do this here. There we go. 3 different sounds. So, we have a beep, a buzz, or a chirp. Beep, buzz, and chirp. And once the phone has beeped, buzzed, or chirped, it can either vibrate slow or fast. So, slow, fast. If it buzzes, it also has the option of slow or fast. And if it chirps, it also has the option of slow or fast vibration. Now, after that, we also have to decide on what kind of light pattern is going to be. Is it going to be white, yellow, blue, or red? White, yellow, blue, or red? White, yellow, blue, red. 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 So thank goodness we weren't dealing with 20 different light possibilities as far as colors go, because that would have meant a lot more complicated diagram. It was complicated enough as it was. So now, how many different ways can this happen? So just to kind of highlight some samples here. You could have a beep with a fast vibration and a blue light. That's a possibility. You could have a buzz with a slow vibration and a red light. You could have a buzz with a fast vibration and a white light. You could have a chirp with a fast vibration and a yellow light. These are all possibilities. So how many possibilities are there? To figure out how many possibilities there are in total, what we're going to do is we're going to count them. That's a possibility, another possibility, another possibility, another possibility. So there's 4 possibilities right there. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. So there are 24 different ways to choose a sound, vibration, and flash. 24 different ways that you can do it. Okay? For some people that want to get kind of funky with their phones, they may have a different pattern for every single person that they correspond with. Maybe their auntie would have a beep, a fast vibration, and a red light. But their cousin might have a chirp, a slow vibration, and a yellow light. So that's how we go ahead and represent the number of possibilities, is with a tree diagram. And we can see that there's a total of 24 different patterns. Okay? All right. And now let's talk about the fundamental counting principle. If there are m ways of doing one thing, n ways of doing a second thing, p ways of doing a third thing, and so on, then the number of ways of doing one of each task is m times n times p, blah, blah, blah. So going back to the last thing that we had, we started with a beep, a buzz, or a chirp. So there were 3 types of sounds, 2 types of vibrations, and 4 different colored lights. 3 times 2 times 4 is 24, which corresponds with the answer that we got. So that's the mathematical or the fundamental counting principle calculation that it would take to represent the same thing that the tree diagram did. If the numbers are big, you're not going to want to draw a tree diagram. If the numbers are reasonable, then a tree diagram would be a perfectly acceptable and reasonable thing to represent it. But if the numbers are really big, then just using the FCP or fundamental counting principle would be the easiest and best thing to use. So let's go ahead and do an example here. A town has telephone numbers that start with a 628 prefix. A sample telephone number would be 628-1234. How many telephone numbers are available? So the town uses only the prefix 628. So that's important to know. And it's also important to know that there are 1, 2, 3, 4 digits after the 628. So here is the question. How many different phone numbers are available? Well, we have 4 digits. And there are 10 choices for the first digit, 10 for the second digit, 10 for the third digit, and 10th for the fourth digit. So it's going to be 10 times 10 times 10 times 10, which is 10,000 phone numbers. So the town can have up to 10,000 phone numbers. Okay? All right, part B. A neighboring town has the 577 and 271 prefixes, so it has 2 prefixes. How many numbers are available in both towns? In both towns. So the first town is what we did in part A. That's 10,000 phone numbers. So we'll say town A, 10,000 phone numbers. Now, it doesn't actually say how many phone numbers in total or altogether. So that leads me to believe that we don't have to go ahead and add the numbers, but just say how many are available in both towns. We could add them together, but it isn't specific enough, so we could also leave it as this is the number in town A, and this is the number in the neighboring town, which we'll call town B. So just so we know, we'll call this town A, and we'll call this town B. Town B. Well, for every prefix, that's a prefix, that's a prefix. We saw in part A that every prefix gave us 10,000 phone numbers. So that should tell us then that there's going to be 10,000 phone numbers here and 10,000 phone numbers there. So to figure out the number of phone numbers in town B, well, it's going to be 10,000 plus 10,000, which is 20,000. So there's 20,000 phone numbers in town B. 10,000 in town A, 20,000 in town B. Of course, if the question asked us how many phone numbers in total are in the 2 towns, we would just add those together, and of course we would get 30,000. It doesn't, so we'll just leave it with the number in each individual town. When we're doing counting problems, it's very important to pay attention to the wording of the question. The inclusion of one word or leaving that same or just slightly different word out could completely change the way that the question would be approached and therefore the answer. So pay attention to the wording of the answer. It's very critical when you go to solve the questions. Okay? All right. Moving on. David wants to go to prom. He has the following: 3 dress shirts, 4 ties, 2 pairs of dress pants, and 2 pairs of dress shoes. In how many ways can David dress for prom? Now, here's the deal. We're going to assume he has to pick one of each. He's not going to go to the prom with a tie, but no dress shirt. So he has to pick one of each. So this goes back to the fundamental counting principle. And the fundamental counting principle is going to tell us that we can find the answer by going 3 times 4 times 2 times 2 and that's going to give us 48 ways. There's 48 different ways he can dress for prom. So now think about this. If you were to get a job in an office or a job where you'd have to dress up, by even changing one part of your outfit, whether it's your shoes, whether it's your shirt, whether it's your tie, or whether it's your dress pants, or any other type of thing. You know, other people might wear pants, top, jewelry. So just, the combinations are endless here. But my point being is by changing one thing, you've got a completely different outfit. So even with a modest number of elements of clothes, you get a lot of different combinations of dress wear that you can have. Now, of course, some colors might not go well together, or you might not want to pair certain things for whatever reason. But the fact remains that still, by combining your pieces of clothing, you actually have a large number of possibilities for dressing. Okay? All right, next example. A student gives student codes in the format of LLNNN, where L is a letter and N is a number from 1 to 9. How many student codes can be made if repetition is allowed? And then how many student codes can be made if repetition is not allowed? So to do this question, and it seems straightforward, but sometimes we have a momentary lapse in our memories and we forget. But just so we know that there's going to be 26 letters in the alphabet. And for the numbers 1 to 9, that would be 9 numbers. So if it's LLNNN, if repetition's allowed, it's going to be 26 times 26 times 9 times 9 times 9. So 26 times 26 times 9 times 9 times 9. So if we go ahead and try and figure out what that would be, what we're going to get is 492,804. If repetition's allowed, that's how many student codes that could be generated. What if repetition is not allowed? Then there are still 26 choices for the first letter, but for the second letter, now you only have 25 choices because one letter has already been chosen. Now by that point, 2 letters have been chosen, but no numbers have been, so there's still 9 choices for the first number. Once one number is chosen, you have 8 choices for the second number and 7 choices for the third number. So this calculation is going to be 26 times 25 times 9 times 8 times 7. 26 times 25 times 9 times 8 times 7. And what we're going to get is 327,600. That's how many student codes can be made if repetition is not allowed. Okay? And last example, here it is. An ice cream shop has the following flavors: vanilla, chocolate, strawberry, butterscotch. How many different cones can be made if a cone has 1, 2, or 3 scoops? So for this, we are going to assume that you could double down on chocolate. If you wanted 2 scoops and you wanted them both to be chocolate, that's totally cool. You want 3 scoops and you want them all to be strawberry? Giddy up. You can do that. But what's interesting here is that some people might go for 1 scoop, some people might go for 2 scoops, and some people might go for 3 scoops. We're looking for the total number of cones that can be made in each scenario. So let's start off with 1 scoop. So for 1 scoop, it's actually very straightforward. It's just going to be the number of different flavors. 1, 2, 3, 4. Easy. For 2 scoops, you have 4 choices for the first scoop and 4 choices for the second scoop. So that's 16 choices or options if you're going to go ahead and have a 2 scoop ice cream. So there's 16 ways of doing that. And if you want 3 scoops, you have 4 choices for the first scoop, 4 choices for the second scoop, and 4 choices for the third scoop. So altogether, for 3 scoop ice creams, you have 64 choices. Okay? So there's 4 different ways to make a 1 scoop ice cream, 16 ways to make a 2 scoop ice cream, and 64 ways to do a 3 scoop ice cream. And then to find the number of ways of having 1, 2, or 3 scoops, what we're going to do is we're going to take these numbers here and we're going to add them. Whenever we're doing counting or probability, which is very directly linked to counting, because in order to find probability, you need to find the number of ways something can happen, and to do that, you need to know how to count. The word or is very significant. When we see or, we often add things. So we're going to add the number of 1 scoop combinations to the number of 2 scoop combinations to the number of 3 scoop combinations. So 4, gotta get the pen instead of the 4 plus 16 plus 64, and there's 84 ways to have 1, 2, or 3 scoops of ice cream. So go ahead, attempt some of the practice problems that are being assigned to you, and make sure to ask for help if you run into problems or you need some clarification on anything from this lesson.